Hello again, hello again. Still people coming in. So I'd like to welcome you to the next talk by Lukas, attacking browsers via WebGPU. Enjoy the talk.
Hello OffensiveCon, my name is Lukas and thanks for joining my session on attacking browsers via WebGPU. Agenda for the next 30 minutes. First of all, I'll introduce this relatively new web standard WebGPU, and in particular we'll focus on how this web standard is implemented within the multi-process architecture of Chrome. Once we have an understanding of this general architecture, we'll next see what are the potentially vulnerable components, in particular which components are processing untrusted inputs directly from the web. Next part of this talk will be about fuzz testing those components, and while I know that not all security researchers in the audience are a particular fan of fuzzing, I hope I can convince you that for this particular job, fuzzing is indeed the right tool. And finally, we'll see how the fuzzer performs against various WebGPU stacks. First, the WebGPU stack on Windows, and afterwards against the WebGPU stack on Android. With that being said, WebGPU in Chrome, it's a relatively new web standard with the idea of exposing the computational resources of a GPU directly to the web. And as such, it is replacing basically WebGL. And yeah, when I mentioned WebGPU in Chrome, of course, I have to have this slide where we see like all the processes in the multi-process architecture of Chrome. And as this audience is probably well aware, vast majority of web content is processed in the so-called renderer process, say HTML, CSS, all these kind of things. And it is a key property of this process, of course, that it is heavily sandboxed, just a narrow system call interface and no access to any of the interesting system services. And the reason being, well, basically this very audience has finding so many bugs in, say, JavaScript engines that defenders decided it is impossible. We need to have some kind of other security boundary that is much more defensible. Also, this security boundary is posing a little bit of a problem in the context of WebGPU because renderer process, of course, has no capability or is not allowed to directly access the GPU. And as such, we have to introduce another component, GPU process in Chrome, which is a privileged process, as in on Windows, for example, the GPU process is only weakly sandboxed, whereas on Android, the GPU process is not sandboxed at all. Coming back to WebGPU, Chrome's implementation is called Dawn, consisting of two components. We have the Dawn client running within the renderer, and we have the Dawn server running in the GPU process, and a communication interface between those two. Now, if web content wants to perform any kind of WebGPU-related API call, more or less all the Dawn client is doing is serializing this API request and sending it over to the Dawn server. And all the interesting processing is happening within the privileged process. Of course, Dawn server is also not directly accessing the GPU, but we have to introduce one more entity here, which is the user mode graphics driver, which sort of acts as a gateway between the Dawn server and the GPU. There are, of course, also some kernel components involved, but we'll not see them today. User mode graphics drivers are exposing some kind of interface, and on Android this interface is called Vulkan, whereas on Windows this interface is D3D. Now that we have this general architecture in mind, it's time to look at the complex pieces of data that are being passed around, and in particular we want to look out for potentially vulnerable components. And if you look into the WebGPU standard, one of the most interesting and most complex pieces of data being passed around are so-called WebGPU shader programs. And generally speaking, shader programs are programs that are designed to be executed on a GPU and not on a CPU. And yeah, as mentioned, Dawn client is just passing them over the IPC interface into the privileged process, and all the interesting processing is happening in there. Now, as mentioned, Dawn server is not directly communicating with the GPU, but instead those shaders have to be passed to, say, the Vulkan interface or the D3D interface. However, Vulkan is not directly accepting WebGPU shaders, and as such, the Dawn server needs to translate them into the respective shading language that is accepted by Vulkan. And this shading language is called Sphere V. And this is also where things are starting to get interesting, because Dawn server is, of course, written in C++, running in a privileged process and directly acting on untrusted web content. However, there's one more translation step that is quite important for the rest of the talk here. The Vulkan interface is directly accepting the Sphere V shaders. However, the GPU can't execute those shaders. Instead, somewhere behind this Vulkan interface, there is some kind of optimizing compiler that is taking the Sphere V shaders and is translating them to the respective instruction set architecture of the GPU on this very device. And this translation step here is happening in some kind of optimizing compiler, but this compiler, it has mostly been optimized for performance, and it has not been designed with this idea in mind, hey, one day this will be part of the one-click surface. Yet here we're essentially just taking those web shaders, translating them a little bit, and then passing them into some kind of compiler that is certainly not hardened for security. Of course, we also have something similar on Windows. The major difference here is that the D3D interface is accepting shaders in the high-level shading language format instead of Sphere V, but the precise differences between those two shader formats will not be important for the remainder of the talk. This already brings us to the second part of this presentation, which is shader fuzzing. And you, of course, could also say, hey, why fuzz test this? I can also read the code. And in the context of Windows, this is actually true. So the shader compiler on Windows is available open source, and you have like 1,000,009 plus C++ code here, and you can find bugs in there. Not necessarily the way I would approach it, but you certainly have the option. However, on Android, things are getting a bit more difficult when it comes to reading the code, because all those optimizing compilers, well, you only have them as binary-only objects. So compilers, like the vendors of the respective GPU stacks, say Qualcomm and ARM, they're just providing you some kind of precompiled shared object, and reading that can get a bit tedious. So I thought, well, it's much easier to write some kind of fuzzer for this WebGPU shading language. With that being said, quick overview of the fuzzing pipeline. First, we are looking into the target we are about to fuzz. And we have those WebGPU shaders. They're entering Dawn server. And in there, we have the first translation step from the WebGPU language into the language that is accepted by the user mode graphics driver. Because we are only caring about the shader compilation for the remainder of this talk, we can essentially extract the component from the Dawn server that is doing the translation and get rid of the rest of Dawn server. We can also perform a similar simplification for the user mode graphics driver here. So on Windows, we take the DirectX compiler, essentially part of DirectX, and extract that. And as mentioned, it is open source, so we can compile it ourselves with all sorts of instrumentation. Next step in the vast majority of fuzzing setups is having some kind of corpus. But this is really easy to come by because, I guess, like in the Chrome repository as an example, there are so many shader files and you can just take them as seeds. Next step is fuzzing, taking one of the files from the corpus and mutate that one. However, this is much easier said than done. And the reason for this will probably be a bit more obvious if we're having a closer look into one of those shader files. What we see here on this slide is a function written in high-level shading, written in the WebGPU shading language. And the syntax here resembles a little bit that of Rust, maybe minus like generics and lifetimes. However, we are still dealing with some kind of statically typed language. And if we are now trying to apply our usual, say, bit flipping mutations you might know from AFL and other fuzzers, you'll just end up with a bunch of broken Unicode. But this shader cannot be parsed by tint, and as such, we are never entering the interesting parts of the shader compilation pipeline. Instead, we need to have some kind of mutation technique that is a bit more clever. And what I've been doing for fast testing here is taking the shader files we have in our corpus and translating them into some kind of abstract intermediate representation. And for those of you who know the talk about Fusilli and its intermediate language, this should sound vaguely familiar. There are, of course, a couple of differences here. And one of the reasons here is that the shader language we're dealing with is statically typed, whereas JavaScript is dynamically typed. So minor differences within the intermediate language. But once we have this intermediate language, the fuzzer is no longer operating on the bits and bytes of the shaders, but instead we can implement mutations on top of this intermediate language. And like first example here is like we can replace a literal with another literal. And of course, you're probably not going to find bugs with this simple technique, but it's just an illustration of what are the things we can do. Another mutation I have implemented here is replacing inputs of expressions with, say, some other kind of expression. And here it becomes really important that the intermediate language is also statically typed, because if we are just starting to replace some kind of expression inputs with an expression of the wrong type, we are just breaking the shader and we are wasting precious compute. Whereas in this particular case here, the fuzzer is replacing expressions with a corresponding or the correct type, and as such we can fully exercise the shader compilation pipeline. Apart from the two mutations we saw already, there are also a couple of more advanced mutations. Say we have code generation mutation, and there's also a couple of splicing mutations. That is pretty much all I have today for the intermediate representation. The next step is, of course, converting the intermediate representation back into the shader language we are targeting. So we take this intermediate representation and translate that to the WebGPU shading language again. And now we can pass it to Tint, translate it to the respective shading language of the backend compiler, high-level shading language for Windows, and then we execute this pipeline. There's just one minor component missing here, and that is the one of coverage feedback. Pretty easy. We just observe the target during execution if there are any kind of bits flipped, because we're exercising new edges, well, we just add it to the corpus, and we repeat that until we run out of compute. Now, this brings us to the first target as of today. And this is the DirectX shader compiler, and like 2 or 3 background facts here. Essentially, the DirectX shader compiler is based on LLVM 3.7. So 10 years ago, Microsoft decided to, hey, we want to have a new shader compiler here. Let's base that on LLVM, because LLVM is kind of cool. And so that is pretty much what happened 10 years ago. And when I'm speaking about DirectX, you can basically think of like some kind of ancient version of LLVM with plenty of Microsoft-specific extensions here. And when developing my fuzzer, I've been using DirectX shader compiler as a target because it's really easily available. You have the source, you can compile it with all kinds of instrumentation, things like that. And quickly after, like just during the development of the fuzzer, implementing like 1 or 2 mutations, well, I already encountered a crash here. Essentially what happened here, we have like this WebGPU shading language translated by Tint to the shader we see here on this slide. And of course it's a bit minimized. This is not like the exact fuzzer output here, but you get the idea. And what happened, we have this main function that is just calling foo. And next step here, foo is just a single assignment statement, as equals as, and of course we have as. And you might wonder, how is it even possible that such a simple shader manages to trigger some interesting behavior in this LLVM plus Microsoft-specific extensions compiler that is known as DirectX? And what's happening here, that LLVM being an optimizing compiler, we are replacing the struct assignment as equals as with the memcopy operation. And we see here source and destination are identical. We have this memcopy as and the size of as. As you might have guessed, well, this entire operation is pretty much redundant, and LLVM being an optimizing compiler will, in a later optimization pass, detect, hey, let's just get rid of the memcopy operation here because we don't need it. And now, after the compiler did that, it's time for the compiler to clean up its internal data structures, which is happening essentially during the compilation of the shader within the GPU process. And the first thing the compiler will do here is now cleaning or clearing up the source of the memcopy operation and second step for the compiler, happening a little while later, is of course also cleaning up the destination of this memcopy operation. And since source and destination are identical, we just end up with the double free. And during the fuzzing, it appeared as a use after free. But it is already quite, it is a relatively trivial bug. And the fuzzer was able to find that by just running it a couple of minutes on my local laptop. And for those of you who might wonder, because we are about to see plenty of more use after freeze, those are not protected by Miracle Pointer because it's part of the DirectX shader compiler, and Miracle Pointer is just in some parts of the Chrome code base. Of course, running any kind of fuzzer on just like local laptop is not an ideal environment. Next step was taking the shader compiler fuzzer and deploy it onto a couple of servers with a little bit more compute, so roughly 1,000 cores, and run that over a month, investing roughly 1 million hours of compute here. And the result of that is pretty much plenty of bugs in the GPU process. Essentially the DirectX shader compiler got obliterated, and it also earned me a little bit of bug bounty money here. And so Google has been quite quick actually in fixing all those bugs, but it has been plenty of work for them, of course, not for me. And one of the interesting things I encountered here during the fixing of those bugs, it turned out that some of them have been fixed in upstream LLVM. So somewhere between LLVM 3.7 and LLVM 20, upstream LLVM said, okay, well, we found some kind of use after free out of bound, let's just fix that. And you might wonder, how come that DirectX shader compiler never backported those patches, because there should have been some kind of security announcement, right? But as a matter of fact, this is not really the case here, because LLVM has some kind of interesting stance on security. And if we are reading the documentation, it's actually pretty clear on that. It says, security-sensitive parts of the LLVM project currently are the following: none. And it is also quite clear, it says, you're not allowed to take any kind of untrusted input and throw it into this optimization pipeline. Clang is not allowed to do that, and DirectX shader compiler is also not allowed to do that, but still, we are taking this web inputs and sort of have this pipeline, and in the end, we end up in the GPU process here. And with this quote in mind, we come to two more shader compilers. And as you might have guessed, both of them on Android also based on versions of LLVM, which are not close to trunk, but a couple of years old here. However, when fuzzing those, there are two problems we have. As I mentioned previously, those shader compilers, they're just available as binary shared objects. We can't really instrument them. And as a matter of fact, we don't have any kind of ASIN instrumentation here, but we still would like to have some kind of strong bug oracle. What I did here for this fuzzing project was just get some kind of pixel device, and on the pixel devices you can sort of experimentally enable memory tagging extension. And if you do that, you have some kind of ASIN-style bug oracle, at least for the heap allocations. Unfortunately, that was not an option for Adreno, because I couldn't find a device that has an Adreno GPU and also supports memory tagging extension, but still you can do a couple of things which make it more likely that you're actually seeing the bugs, for example, by placing allocations at the end of a page with the poison page next to that, or clobbering allocations on free. However, as mentioned, there are two problems here, and the next one probably will be a bit more obvious if we are having a look at this shader compilation pipeline once more, this time with the Qualcomm shader compiler. And the problem here, of course, is that we are lacking any kind of coverage signal, which also prevents the fuzzer from steering the corpus development into any kind of interesting direction. So what we need here is some kind of technique that allows us to regain the ability to collect coverage signal. And this is what the next part here will be about. So we have all those conditional branches in those binary shared objects, and just like a rough ballpark here, we're speaking about, in context of the Qualcomm shader compiler, about like 500,000 of conditional branches, which leaves us with 1 million edges here. Now, the approach I took here is essentially loading the fuzzer target, the Qualcomm shader compiler, into memory, and then in memory rewriting the target. And essentially adding some kind of additional instrumentation that allows me to see the execution of the respective edges. And disassembling in memory, it is quite easy because we are speaking about ARM64 architecture, which also means all the instructions are 4-byte aligned and you don't have this x86 madness or jumping into the middle of instructions and these kind of things. The only thing that would kind of prevent that would be if there was some kind of data embedded into the text section, but it seems that compilers are no longer doing that. Now, identifying the conditional branches in memory is pretty easy. And for each of the conditional branches, we can allocate some kind of stub region, and in there, we are replicating the respective conditional branches. Once we have that, we can override the conditional branch, the original conditional branch, with an unconditional branch, and within the stub region, we can emit some kind of coverage instrumentation that on exercising the respective edge will set some kind of bit within the coverage map, and the fuzzer can use that to develop its corpus into interesting directions. Of course, also we have to rewire back this instrumentation back to the original branch label and do that as well, not only for the not only for the non-taken variant, but also for the taken variant of the conditional branch. Now, coming to the results of this, I've been deploying this fuzzer with my sort of caveman-style coverage instrumentation on 2 devices, as mentioned, one of the Pixel devices and another device with an Adreno GPU. In total, it found 4 issues on those 2 devices, 2 issues in the Mali GPU stack, essentially, and 2 of them in the Adreno GPU stack. And here, again, we are seeing a similar pattern that also affected the DirectX shader compiler. One of the issues in Mali was the use of the free that has been fixed somewhere in upstream LLVM. However, ARM did not recognize this patch as being some kind of security relevant, and as such, it has never been backported to their a bit dated version of LLVM. And I did not encounter this pattern for Adreno, but still you can find a few issues in there. And this also brings me to the update situation on Android, which is of course a little bit more complicated, because what's happening here is, if you report it back to the vendor, say Qualcomm or ARM, they will of course eventually provide a fix, but those fixes will not directly be distributed to the affected devices, but instead they will be sent to the device manufacturers. And those device manufacturers may or may not distribute some kind of over-the-air update. It really depends on whether your device is still receiving updates. Of course, this is kind of a problem because there are a couple of devices out there, and potentially millions of devices here, which will not receive any kind of fixes for those reported issues, which brings us to the potential workarounds. And one of the things the Chrome team here tries to do is identifying those patterns that might be problematic for the backend shader compiler, and then on top of that implement some kind of workaround such that it's becoming impossible to trigger the bug. However, this turned out to be really, really difficult, and it has been just, so the Chrome team just succeeded in 1 out of 4 cases, which also means for 3 out of 4 cases, there are no workarounds in Chrome, and devices might not get fixed at all. This is pretty much the end of the past research, and I'd like to use the remaining time here for going a little bit into future research here. And one of the things here is, I summarize that as pathological inputs. See, so far the fuzzer is quite capable of generating valid shader files. However, those usually don't exhibit any kind of pathological behavior. Say, for example, generated functions have between 0 to 5 parameters, but compiling functions with 0 to 5 parameters is basically bread and butter of LLVM, and it's not super likely that you're experiencing or encountering any kind of weird behavior. However, the specification also allows you to have functions with many, many more parameters, and those might hit code paths within LLVM that are exercised way less often, but fuzzer is currently not generating such inputs. Next part for further research is supporting additional backends. So so far, we have the Dawn server entering the Mali and the Adreno stack via Vulkan, and we're testing this DirectX shader compiler coming from Microsoft. Microsoft's output, so the output of the LLVM shader compiler, is LLVM 3.7 bitcode. And this bitcode is passed to the respective GPU stacks of NVIDIA, Intel, and AMD. And I really believe that within those backends there will be interesting code paths you should be able to hit if you manage to harness all that properly. And last part for future research here is so-called WebGPU compatibility mode. And the motivation here behind this, say, optional extension to the WebGPU standard is that plenty of Android devices don't support the respective Vulkan interface needed for a WebGPU implementation. Instead, what compatibility mode will do is implement WebGPU on top of OpenGL, and this will allow to target more devices via WebGPU, and it can potentially even open up additional pathways into the existing shader compilers that have been tested so far. And due to this vast complexity that will even increase in the future due to, say, compatibility mode, I'd like to share one more quote, this time from the Chromium technical report on WebGPU, and it states, user mode graphics driver complexity could reach a point where it becomes indefensible. And let's see where we'll end up there. And this is pretty much end of my talk. So in total, we found 21 bugs in web-exposed components. There will be more attack surface in the future. And this work has been done mostly in context of academia. So there's also a paper on this topic if you're interested more. And some parts of the fuzzer are actually open source. So the fuzzer and the Windows components, the Android components are not open source though. That's all I have. Thanks.
Do we have any questions? Thank you so much for the talk. Cheers.
Thanks.
I have a question. Thanks for your talk. I have a question about the fuzzing setup. So I assume you compiled all the components into a custom target and ran it under your own fuzzer. Yeah.
Yes.
Okay.
But
Thanks. Yeah. Okay. Thank you.